Welcome back, Gen Chem, to the next section of our organic chemistry excursion. We are at 21.2, unsaturated hydrocarbons. So we talked about saturated, as in we have a carbon chain that has 100% single bonds, no double bonds between the carbons at all. So what we mean by saturated is this is saturated with the maximum amount of hydrogens. Now, what if, though, instead of having hydrogens here, these electrons are now being shared to form a bond between these two carbons? So this is another form that this could take. So I'm going to put two bonds between those two carbons. This one over here still has all these H's. We still have these H's down here. But notice 1 bond, 2 bond, 3, 4. Carbon is surrounded by 4 bonds. Carbon is surrounded by 4 bonds. Its octet is full. This is now an unsaturated carbon. It could have more bonds here, and here, but it's bonding to itself. So saturated versus unsaturated. So if there's any double bond or triple bond in a carbon chain, we call that an unsaturated hydrocarbon, regardless of the number. So fully saturated, any amount of bonds that are double or triple, we call this an unsaturated carbon. And I just said quite a bit of this, but let's take a peek at this. Alkene, and we call them alkenes. That's the specific name for them. Instead of alkane, if we see an ENE, we know that this is some sort of double bond in between them. So double bond specifically means alkene. And they take on this form. So remember, it was 2N plus 2 hydrogens for a straight chain or a general alkane. Well, we lose those plus 2. So if the carbon chain is 5, there should be 2 times that number of hydrogens. And we'll talk about the planar nature of these when we look at some of the actual pictures. So how would we draw a hydrocarbon? Well, a couple different ways. We could see it in this condensed version like this, where it's just CH2, CH2. Remember, these bonds are not to the H's, but to write out a condensed structural formula, we would do that. Here we're actually showing the bonds. This is a more, I would say, better representation of this, because this shows the actual sp2 120-degree angles for this type of bond. If you go back to this slide here, it says the 2 carbon atoms involved in the double bond are sp2 hybridized with 120-degree bond angles and trigonal planar geometries. So when we learned about Lewis structures and predicting geometry, this carbon center right here has 3 things bonded to it, 3 bonding groups and no lone pairs. That means the lowest energy stabilization it's going to take is this 120-degree bond angle between all of these. So it's a flat molecule. This is looking at it top down here, 100% flat molecule. And remember, why is it flat again? Well, I'm going to turn it to its side. And remember, the bonding picture looks like this. We have p orbitals up here and up here. So these are a p orbital. So these are my H's. I'm going to delete this. Here are my hydrogens. Remember, a double bond is a sigma overlap in the middle, and then a pi overlap top and bottom. That's the 2 bonds. So you can't turn this molecule. If you try to turn this, you'll break this double bond. So this is a flat, planar molecule. So that's how we represent something like ethene. Ethene, by the way, the most simple, it's the smallest alkene because you have 2 carbons and then you form a double bond. And by definition, now that's an alkene. We have to have 2 carbons to do that. So we have the H's like this. Ethene is a very important molecule. It's the most simple. I did a little bit of Googling, 150 million tons. Notice this is TONNE. It's not a fancy way of writing tons. It's a specific thing. That's 1,000 kilograms. not the English ton, T-O-N. So 150 million times 1,000 kilograms of this stuff is produced per year. And about half of that used to produce plastic, polyethylene. Plastic, it's a polymer. So double bonds are typically used to move those electrons to another chain to form polymers, and you continue this process. So very, very important molecule. Polyethylene plastic is the most common type of plastic, and like over half of this 150 million tons is used for that plastic. So I thought it was just a good idea to point out that this is not just some random molecule in the world. This is something that we use every single day in the form of a polymer in a plastic. So that's how we would draw this ethene. So how do we name them? So we learned about naming alkanes before. How do we name alkenes? It's pretty similar. It's just that this double bond really takes precedent over our numbering system. So notice we don't have any substituents here. That's fine. We're really just focusing on naming something with a double bond in it. So we still need to find the longest continuous chain. But importantly, find the longest continuous carbon chain that includes both carbon atoms of the double bond. So actually, I'm going to change this to on. I would not want to number this 1, 2, 3, 4, 5, because I want to keep the longest chain that includes my carbon here, or sorry, the double bond. So instead, I want to number this as a 1, 2, 3, 4. This is a butene. This then becomes a substituent instead. So this is not part of the parent chain. This becomes an ethyl group, a substituent. So that's really important when naming alkenes. This takes precedent over the numbering. We want to keep that in the longest chain. So this is a but and not a pent for this chain here. Okay, so rule number 2. What about actually the name itself? So this says indicate the location of the double bond when necessary. Select a numbering system that gives the double bond the lowest number possible. So just like substituents, we want to keep the numbering system 1, 2, 3, 4, and not 1, 2, 3, 4. We don't want the double bond at the 4 position. We want to minimize that. So we want to start our numbering at the 1 position there. So that is what we're going to name this. So how do we name this? Well, our double bond is tied up in a 4 chain here. So this is going to be a but. It's going to be a not a butane, but a butene because of that double bond. So then we have to think about where are substituents and where's the double bond. Well, this over here is an ethyl group. So that's a substituent, and we need to tell everybody where that lives, and it lives at the 2 position. So this is going to be 2 ethyl, 1 butene. 2 ethyl, 1 butene. 1 is telling us where the double bond is. The double bond is at the 1 position. It starts with that first carbon, and it goes to the 2. So we call that 2 ethyl, 1 butene. And if we look at the first 4 of the unbranched alkenes, so just like the straight chain, something with a double bond in it, here's ethene. Prop, so we have 1, 2, 3 carbons here. Notice it's not 1 propene. We don't need to call it that because if you put the double bond here, it's the same molecule. So this is the 1 position, or this could be the 1 position. So we just call this propene. That's very simple, propene. Now, what about butene? Okay, in butene's case, though, we actually had to indicate it's at the 1 position because we can also have another possibility, 2 butene. Notice there's only 2 possibilities for butene. You either have the double bond here or you have the double bond in the middle because it's symmetrical. If I put the double bond over here, that's the same thing as having it there. These are equivalent because you can just flip that molecule over. So there's only 2 possibilities here for butene. This is the 1 position, and this is the 1, 2, 3, 4 chain, 2 position. Notice if I labeled this the other way, 1, 2, 3, 4, it doesn't matter which way I number it, it's still the 2 position. So there's 2 butene. So let's practice naming a couple of these simple cases. So using the naming rules, give the video a pause again if you're comfortable, and try to think about how you would name these alkenes, remembering that you need to indicate where the double bond is. Okay, we are back. Let's take a look at these. First one, pretty simple case here because, well, actually, it might be a little confusing because these are now condensed. So sometimes for me, it just helps to draw out the structure a little bit, but we don't necessarily need to. Let's just continue on with this example. So how long is this? Well, there's no branching here, so this is just 1, 2, 3, 4, 5. Notice I could have labeled this 1, 2, 3, 4, and 5. Now remember though, I want to show where the double bond is on the lowest number. So that means it's at the 2, it starts at the 2 position here. If I number it this direction, it would start at the 4 position. I don't want that. So I need to number this 1, 2, 3, 4, 5. So that's a pent, and it's going to be a pentene, indicating there's a double bond in here. Now I just indicate where the double bond is at the 2 position. So this one should be 2 pentene for A. All right, let's look at B then. B, same thing. We need to think about how long this chain is first. And I can number it from this side and going this direction or this direction. And since I see a double bond here, I want to minimize where it is on the numbering scale. So I need to start here with a 1. So this is going to be 1, 2, 3, 4, 5, 6. So this is a hexene. Hex for 6. Part of getting these correct is memorizing these prefixes. So if you don't have those memorized, you got to go back and get that done for sure. I'm gonna have a sip of coffee here, just like we're in class. Wouldn't be class if I didn't interrupt with a coffee sip. All right. Let's take a look. Okay, this is hexene, and now we need to tell you where the double bond is. Double bond is at the 1 position, starts at the 1 position, so we just call this 1 hexene. And whoa, what's down here? This might look familiar. Well, let's pretend we don't recognize what that is. I mean, I recognize it, but systematic naming though, this is a 1, 2 carbon chain, so it's eth, and then ene, because there's a double bond. By the way, you do see this compound called ethylene a lot. It's its common name, but the international, the standardized name is ethene. So I forgot to mention that. Polyethylene plastic. They usually call it polyethylene, not polyethylene. So I want to make sure I mention that. Okay, and then why don't we have to call this 1 ethene? Well, because it's unambiguous. If I see ethene, I know it's 2 carbon. There can only be 1 double bond in the middle, so we just call this ethene. All right. Let me see. Okay, so now we learned how to name, systematic naming of our alkenes. Let's move on to some reactions. So we looked at some reactions. There are answers. Hey, I'm right. Look at that. We looked at some reactions last time of alkanes, and we're going to look at some similar reactions and see how they react. So reactants. So we were looking at halogens before. Yeah, like Br2, Cl2, I2, etc., reacting with alkanes. We saw that they could replace hydrogens. Alkanes undergo something called an addition reaction. So what we're doing is adding bromine to both of those carbons. So we're not replacing hydrogens this time because we have extra electrons in here. Remember, there's 2 electrons, actually 4 electrons, sorry, tied up in this bond. 4. So these electrons can go make a bond with something, and those electrons could too. So leaving a single bond in the middle and forming 2 new bonds. So we call these addition reactions. You'll hear the terminology like bromine was added across this double bond. So there was an addition across the double bond to give you two new bonds to bromine. So that would be a case here. So hydrogen, before we looked at this and they were adding it to the carbon center one at a time. Now we're adding both. So that's one reaction that these go under. Besides that, if we have Br2 we had before, what about HBr? So these are basically hydrogen bromide gas. So we have this gas compound, not a liquid acid in this sense, but if you see HBr gas plus this gas, you'll see the same addition reaction, but this time you're going to add an H and the Br, kind of like the Br and Br. So that's another way we can get an addition reaction with alkenes. Another very common reaction is, importantly, using an acid catalyst. We're not going to get into any type of mechanisms here, but if you have water with H plus catalyst around, so an acidic catalyst, you can form an addition reaction and form an alcohol. So now we can actually form an OH group on this carbon and an H over here, and this now becomes an alcohol. OH substituent takes on precedence. This is no longer just a simple alkane. Because of the OH group there, we just formed an alcohol there. And notice this is CH3, CH2OH. This indeed is ethanol. But that's naming for another time. So we call that a hydration reaction. We are adding water across the double bond. It's an addition reaction, but specifically a hydration reaction. If you see hydration, you think, okay, I'm adding HOH, H2O, across that double bond in the presence of some sort of acid catalyst, though. This reaction is extremely important, and especially in the world of food. So if you take butter, it has fats in it that have groups that, and I'm using the skeletal form, but they have these bonds in there that look like this. Whoops. These are called unsaturated fats. That's where we get the saturated versus unsaturated fats. Saturated fats are those that have 100% single bonds in their side chains. Unsaturated fats have these double bonds, and they're healthier in a sense, but your body does need both saturated and unsaturated fats. But saturated fats stack up a lot closer next to each other. So butter at room temperature is a solid versus olive oil at room temperature is a liquid. The saturated fats stack up next to each other and form solids much easier than unsaturated fats. So what if you wanted something in the middle of between like olive oil, butter versus olive oil? You want something in between. Well, what they actually do is do this hydrogenation reaction. They are going to take your unsaturated fat and do a hydrogenation reaction. We're going to add H2 gas, but using, very importantly, a catalyst, and we're going to add H's across the double bond. So we can turn the unsaturated fat into a saturated fat. But in the food industry, they'll take something like, whoops, oil, whatever it is, maybe canola oil, and partially hydrogenate. So at the end, you have a mixture of saturated and unsaturated fats. And that's like more of a spreadable margarine type of system. So Crisco or margarine, those spreadable butters, it takes properties of butter and oils, and you make this partially hydrogenated mixture of something like, say, canola oil or olive oil, something like that. So hydrogenation is very important in the food industry. But that's how you would add hydrogens across a double bond. You take hydrogen gas, a nickel catalyst. Again, it's another addition reaction, but we call it hydrogenation in this case. Okay, that's our discussion of alkenes. Now let's move on to the next step of unsaturation, and that would be alkynes. So just like alkane, whoops, and then we went to alkenes and alkyne. So this is all single bonds. This is where we have a double bond. Wow, let's try that again. And alkynes are the word we use to show triple bonds. So for their general formula, so for alkane it was C something, that's whatever it is, how many carbons you have, and the H is 2 times that number plus 2 extras. Then we went down 2 carbons for alkenes. It was CN H2N. Finally, for alkynes, it's CnH2n minus 2. So even to where 2 more carbons are gone now. So now it's an additional bond between 2 carbons. Now remember, these type of carbon centers are sp hybridized, and they have a linear geometry. They are locked in place right across from each other, and there's 180-degree bond angles between them. And ethyne is the simplest. Instead of C2H4 for ethene, see, we've dropped 2 more hydrogens. Now we're only just down to 2. So if you see C2H2, you know that there's got to be a triple bond between those carbons. And ethyne is a gas at room temperature, and we use that a lot in welding, high temperature welding. So naming, we use "-ine" instead of "-ene" to name these. So let's look at acetylene or ethene, or ethyne rather. So this is the common name, like an acetylene gas torch, but ethyne is the proper scientific name, but acetylene is probably used more often than ethyne, to be honest. So 3 representations, just like we were looking at ethene before, just the condensed where you have the CH stuck there, and then this shows you actually the bond. And remember, this is locked in place. This is flat 180 bond angles. If you would build that out, it's completely flat and locked. And then that's due to the hybridization again. And I could try to draw this again, but it's kind of a mess. But in this case, we have carbon and carbon. You've got a sigma bond in the middle. That's one bond. Let me change my colors here. You've got another bond coming from this p orbital set. And then you have another that's going out of the plane. You've got another p orbital back there overlapping in space. So you've got that pi bond back there, and this pi bond right here. And then you've got finally your final sigma bonds to the hydrogens right here. That yellow is maybe not the best choice. And yes, that's a mess. We can go and look that back up. So we've got our 3 bonds here. There's pi overlap here. That's a bond. There's pi overlap back here. That's a bond. And then a sigma overlap in the middle. So we got our 3 bonds. 3 bonds. And we say this is sp hybridized at that carbon center to do that. It's hybridizing its orbitals and leaving 1 for the sigma bond over here. So there's our representation of that. Just a little review of how those are bonding together. Okay, reactions are very similar, like alkenes. You can do addition reactions. Notice though, instead of just 1 mole of Br2, you can add 2 moles across this double bond, or triple bond. So there's electrons that go out and form bonds with this, and then there's electrons that go out and form bonds with these, and you get all of these bromines attached to that molecule. In the same way, you can do hydrogenation reactions with a catalyst, but you can add 2 moles of that to get all the way to saturated alkane over here. So very similar to alkenes. So how would we actually name these compounds now? So now we're kind of just comparing an alkene to an alkyne. It's the same type of naming, except we're just going to use "-ene" for something with a double bond and "-ine". Otherwise, you name them exactly the same. And notice this says, name the following compounds Then write condensed structures for the products formed when 1 mole of each reacts with 1 mole of Br2. So I'm going to give you guys a chance to pause here. Go ahead and pause this and try to work this out. First, work through the names, and then see what you can do to predict the condensed structures of the actual products that form. Okay, we are back. Let's check out the names first. First step, we need to see, we identified, yeah, there's a double bond right here, but now we need to number it. So there's 3 carbons, and again, I can either number it 1, 2, 3, or 1, 2, 3. We want to start with this one here to minimize the number of where the carbon is. So we want to start the double bond at the 1 position, not name it at the 3 position. So that's the numbering scheme that we want, not that one. So then we think about what is 3 carbons long. That's a prop. And this, what's the last part? This is a double bond, so this is propene. Finally, we need to tell you where the double bond is. In this case, it's at the 1 position, so we could call this 1 propene. However, we can also simplify this. This isn't technically wrong, but it's a little bit better to call this just straight up propene. We're always trying to simplify our naming if we can. Why can I call it that again? It's because it doesn't matter if I put this double bond here or here. That's still the 1 position. It's the same molecule whether I put it there or there. So I don't need to tell you it's a 1 position. There's only one place where the double bond could go, the 1 position. So I would call that 1 propene, or just propene rather. Let me clean this up. Okay, now what happens when I add 1 mole of Br2? And for me, it's a little bit easier to draw this out again. So let's just draw carbon. So this is CH3, 1, 2, 3. Carbon, H, double bond, carbon, CH2. So there's our molecule. So where is this Br going? It's going to add across this double bond. So remember, it's an addition reaction. I'm not replacing things like I was with alkanes. I'm just simply using these electrons to go form a bond from this carbon to something and this carbon to something. So I need to form a bond to Br here and bond to Br here. So what that would look like, I would erase that double bond, Br and Br. So how do I actually write the condensed structures for this? Well, you just simply write out what you see. So let's try that. Let's convert that into a condensed structure. So first, what is this? That's a CH3, so I'm going to write that down. Then what do I see here? Well, I see a CHBr or CBRH, but by convention, we write the H's first. So we're going to call this CHBr. And then moving along, what do we see here? Well, we see CH2Br. So that's what I'll write. Yeah, I'm not a big fan of condensed structural formulas like this, condensed structures. They're just kind of messy, but you know what? That's how we would write it condensed. So you just kind of write out what you see, including the CH's first, and then write them out. And okay, let's look at the next one. Next one, what do we have here? We have let's count how many carbons we have. 1, 2, 3, 4, 5, 6. Okay, 6. And how do we want to number this? Well, we want to start the numbering here, 1, 2, 3, to make sure that we minimize where that triple bond is going to be. So now the triple bond is at the 2 position. That's where our triple bond is going to be. So naming wise, what would we name this thing? Well, it's 6 would be hex. And it's not hexene, this is hexine. Looks kind of weird. It is kind of a weird looking name. Hexine. And now where is the triple bond? It's at the 2 position. So 2 whoops, good old 2-hexyne. So we're starting with 2-hexyne. Okay, now what are we going to do? We're going to add just 1 mole of Br2. Okay, 1 mole of Br2. And really, again, if we look at this, where's that Br2 going to go? I'm going to erase some things here. Just like up there, this is going to form a bond to Br and Br. And you're going to get rid of one of those bonds here. Look, notice this is just 1 mole of Br2. So we're not adding multiple amounts here. We're just adding 1 mole. So in terms of the name now, we can kind of sneak around drawing out the entire structure, although we can. Let's just try to write this out knowing that that's what it's going to be now. That's where it's going to add those two. So the structure will just be CH3, CH2, CH2, and now what's this? Carbon bromine. That's a CBr right there. CBr bonded to another CBr, but what is the bond look like in the middle now? We took away one of those bonds, so this is now a double bond. CBr, CH3. But you know what? I would like to draw this out. Let's draw this out as practice. Get rid of that. So as practice for you, go ahead and pause and draw this out like this. Draw it out in this manner. That's also really good practice converting these to these more full structures. Okay, now I'm going to draw it out myself as well. So I'm going to draw this out. Carbon, HHH, carbon, HH, carbon, HH, bonded to a carbon, which is triple bonded to a carbon, which is bonded to a CH3. So this is just good practice too, getting in the habit of seeing the full picture. Okay, then what's going to happen? I'm going to add a bromine across this triple bond. So that means I'm going to be forming bonds here. I'm going to get rid of this one and get rid of this one. There we go. That's my new structure. Now I have, and keeping my double bond there. If I wanted to react this with 2 moles of bromine, I could also do that, but this problem said 1 mole. But 2 moles, you do the same thing, but now I can add even more of these. And you get rid of that single bond there, or that double bond to make it a single bond. But this is the problem that we have here. So again, if I wanted to just write this down to the condensed version coming from this structure, I'm going to look at each one of these carbons. CH3, then this one is CH2, this one CH2, this one CBr. But when there are double bonds or triple bonds, we write those out. Notice we don't write the single bonds in condensed structures, but we will for this. Double bond to another CBr, and then finally CH3. And the PowerPoint actually goes ahead and names these compounds too. So let's go ahead to the next slide and go through how we named those. Okay, so here are our products, and it says, it doesn't actually ask you, it says name the following unsaturated hydrocarbons, but it went ahead and named these anyways. So let's see how we do that here with some more substituents here. So how do we name this compound? Well, we went to, like before, we went from propene. We lost the double bond, so now we're using propane as our parent name. And what substituents we have? Well, we have at the 1 position, we have a bromo, and at the 2 position, we have a bromo. It helps to actually draw this out to see where those actually bromines are. Let's do that. CH3 carbon H Br, right? So here's our CH3. This carbon is attached to this carbon and also has an HBr on it. That's connected to this carbon, and that has a CH2Br. Look to the right to see where that stuff is. So if we're naming this, we need to say that there's a 1, whoops, I'm gonna make this red. The 1, 2, 3 position here. We have a 1, 2 dibromo propane. So that's how we got from that to that. Let's check out this next one. We went from a hexyne to a hexene. Notice the 2-hexene still shows where that double bond is. That didn't change that. 1, 2, 3. So what do we say for this one? Well, now we need to indicate, first of all, that it is a 2-hexene, but also where the bromines are, and they're at the 2 and 3 position. So it's going to be 2, 3 dibromo 2-hexene. Notice the substituents go over here, and the 2 goes last to show where the double bond is. So that's how you would name those compounds there. Okay, I'm going to stop the lecture for part 1, and next time, part 2 of 21 point, where are we at now? 21.2? Correct. We'll start with aromatic hydrocarbons, and then we will finish off the rest of the chapter looking at how those react as well. So I'll see you guys next time for part 2 of section 21.2.